Today we are exceptionally fortunate, very, very fortunate and absolutely delighted to welcome Dr. Dalia Ghanem from the University of California, Davis, to talk to us about evaluating the impact of regulatory policies on social welfare in different settings. We have been looking for a distinguished scholar that can guide us into the scientific work of evaluating regulatory policies and programs. And we are very fortunate that Dalia and her colleagues would agree to come and make the presentation today. It is very much in order that I introduce Dalia formally. Many of you will have met her, or at least will have met her work, her publications. Dalia is absolutely energetic, very active in the econometric society environment, and particularly so using her energy to support the econometric society African region. We are all very proud of the work she's doing there. But full-time, she's an associate professor of agriculture and resource economics at the University of California, Davis. She's pushing very, very important work, especially spanning econometrics and environmental economics. Has special interest in evaluating, and again, I want to emphasize the word evaluating, environmental policies and climate change impacts. This is a very topical, working on very extremely very urgent and very important issue today, as climate risk is now rated #1 globally. Now, as part of Dalia's work, she keeps on pounding away, developing very exciting, innovative research methods for non-parametric panel models and the application to difference designs and randomized experiments. So we are getting very, very scientific contributions today from Dalia and her colleagues. Her work has also provided methods relevant for environmental economists, particularly with respect to the distributional impacts of regulatory policies, as she will be doing, showing us here, with the use of mixed and high frequency panel data, threshold manipulation in environmental monitoring. She's gonna take us today through all that scientific work, and with the great potential of influencing some of the research we're doing in many fields. Indeed. She's also very active in leading scientific work. She's co-editor of the Journal of the Association of Environmental and Resource Economics. And as I mentioned previously, she uses her very tremendous energy, high energy, in influencing the work in the African Regional Standing Committee of the Economic Society, where I have had exceptional pleasure of working with her over the years. Dalia and a PhD in economics at the University of California, San Diego, in 2013. Then she had, before that, completed an MSc in econometrics and mathematical economics around this neck of the woods here at London School of Economics in 2007, and a BA in economics and political science at the American University in Cairo in 2003. So please join me in putting your hands together and welcoming a stand leader in this area of evaluation, Dalia, to share her work with us today. We are absolutely delighted, and it's been a pleasure to work with her over the years. And today, she actually does me the honor of being able to be the chief guest here. This is for Global Finance. Dalia, you are much welcome.
Thank you so much, Victor. Thank you for the really kind and generous introduction. It's been really a pleasure to also work with you throughout the last few years as part of the Econometric Society Africa region. And thank you very much for this kind invitation. I'm really excited to share this work, which is joined with Désiré Kédagni at UNC Chapel Hill and Ismael Mourifié. I want to, before I get into the paper, I want to kind of give you an idea of the backdrop of this work, which is that difference in different settings are very common in many policy evaluation settings. And of course, while a vast literature has recently grown, trying to examine how to account for heterogeneity in treatment effects when you're estimating average treatment effect type objects. The literature has therefore focused a lot more on heterogeneity in terms of the conditional mean, or how to account for heterogeneity in averaging over treatment effects of various individuals or groups. What we're going to do here, and this departs a little bit from this recent literature, is to refocus our attention on counterfactual distributions. The main motivation behind this is that really many regulatory policies impose thresholds or minimum or maximum standards on outcomes of interest. Minimum wages are a very widely used policy in labor economics. Minimum and maximum working time is another type of this policy. In health and safety, minimum safety standards are obviously widely used. There's also in environmental economics and actually climate policy, thresholds play a very important role. In fact, reporting and action thresholds are widely used in pollution monitoring to induce different frequencies of reporting or action to mitigate pollution. So when we think about meeting the challenges of climate change, these regulatory policies are extremely important, and to be able to assess their impacts adequately is crucial. So to motivate the types of implications that these policies have for the outcome distribution, I want to revisit this picture here from a recent QJE paper that studies the impact of the minimum wage. Okay, and basically this paper shows you, this figure shows us here that it's from their conceptual framework, that this red dotted line is basically the density of the wage distribution without a minimum wage. Okay, and then when we introduce a minimum wage, we see that there is bunching at the minimum wage here, right? So as a result, what we expect from, and this picture really shows this very well, is that bunching is very common in these types of regulatory policies or in the outcome distributions that we are trying to assess the impact of these policies on. Okay. The other thing that is very important, and perhaps more important to keep in mind here, is that these types of policies might not actually affect the whole distribution, but rather only part of it, right? So as a result, if we just look at the average, we may not fully capture the impact of such policies. And therefore, this really motivates our goal here, which is to identify the outcome distribution or the counterfactual distribution in order to be able to obviously look at the average if we want to, but also look at other objects of interest that are crucial to characterize the impact of those policies on social welfare. And while I'm going, I really welcome questions along the way. So, I know this is like, you'll see in a bit, it will become very technical, but I'm happy to answer any questions. And, I would be, I actually appreciate questions throughout the talk. So no need to wait until the end or whatever, okay? Great. So the existing literature, and specifically focusing on fully non-parametric approaches to identify these counterfactual distributions, cannot allow for several features that are crucial in the contexts we care about. First, the possibility of mixed outcomes, which means that we have part discrete, part continuous distributions, non-random selection into treatment, And finally, time variability in the potential outcome distribution for the same subpopulation across time. So to provide, there are two candidates that potentially, are worth thinking about here, and I will explain why each doesn't fulfill all of these criteria. Distributional difference in differences typically requires, as a recent paper in Econometrica showed by Roth and Santana, either random assignment, time homogeneity of the potential outcome distribution, or a mixture of the two, okay? Where one subpopulation obeys random assignment, but another obeys time homogeneity. These are obviously very restrictive assumptions in practice, and they don't typically allow for the settings we care about, which are typically there are non-random selection into treatment. We don't really think that, some subpopulation is randomly assigned and another kind of doesn't change its outcome distribution. We typically think that there is non-random selection into treatment as well as time variability in the potential outcome distribution, okay? And then finally, the changes in changes approach, which was introduced in the seminal work by Etienne and Vince in 2006, that allows for non-random selection into treatment and time heterogeneity in their identification results, but they provide results for continuous and discrete outcomes, but not mixed, which are going to be important in our context here. So for all of the above reasons, what we want to do in this paper is basically to propose a unifying partial identification result that can apply to any type of outcome distribution, whether it's mixed, continuous, or discrete, that does not restrict variability of the marginal distribution across time. That's also going to be invariant to monotonic transformations because it's an important property of identifying assumptions. And finally, that it can apply to either repeated cross-sections or panel data, because oftentimes in the policy evaluation settings we are interested in, we will typically not have a panel data. Okay? Now, our bounding approach will rely on a novel assumption that we call copula stability, which will rely on basically the stability of dependence between treatment assignment and the untreated potential outcome over time. And once we have used this assumption to identify the counterfactual distribution, we also propose social welfare treatment effect parameters that can allow us to quantify the impact of the policy on social welfare, and particularly inequality in the lower or upper tail of the distribution. So I'll pause here in case there are some questions.
Not yet, Dalia. I think we are good.
No, I just thought I'll give a pause just in case. Okay.
Yeah, sure. Yeah.
Okay, great. There's, of course, a large and growing literature that we're contributing to. As I mentioned, the classical and recent difference in difference literature is very relevant here. Most of that, of course, focuses on average treatment effect, as I mentioned. There's also a literature on the issues with the parallel trends assumption in terms of its lack of invariance to monotonic transformation, as well as connection to selection into treatment, that also we speak to some extent as well in this paper. Where we contribute exactly is actually thinking about alternatives to parallel trends, but I want to emphasize that our goal is not just to get another assumption that's not parallel trends, but rather, because we change the object of interest, we don't just care about the average treatment effect on the treated, but rather the whole counterfactual distribution. And as a result, the parallel trends assumption will no longer be sufficient to identify this object. Okay? And particularly, so we're building on a strand of the literature here that has focused also on counterfactual distributions and their identification. Finally, there is a literature that's, because we use copula in policy evaluation setting, there's a few papers in the literature that have also used copula in policy evaluation literature, in the policy evaluation literature that are also important to mention here, and their insights have also been helpful. So now, just to give you a broad roadmap of where we're going, so I'll first set up and give you our notation. Then I'm going to move on to the main identifying assumptions, and particularly try to give you as much context to that, and how you use some examples to motivate it. Then I'll move on to the partial identification result and the social welfare treatment effect parameters, and I'll conclude with our application, where we actually revisit the minimum wage QJE paper that I mentioned before. Okay? So for the purpose of this paper, we primarily are focused on the two-group potential outcome setting, where we have kind of the canonical difference in difference design. So in the first period, period 0, we observe Y0, which equals to Y00, which denotes the untreated potential outcome in period T, okay, which is period 0. So just because I know our notation is slightly it's slightly difficult because we have this like two subscripts for T and D, and partly because of, as you will see, our outcome will be in subscripts a lot. So if we don't, it will look if it's too big, it will look too complicated and not as neat. So the first YTD stands for T, stands for the time period, D for the treatment status we're referring to. So for the potential outcomes, the first index is referring to time, and the second to treatment status. Now in the post-treatment period, period 1, we observe Y1, which equals to Y11 if you're in the treatment group. So it's the treated potential outcome in period 1, or Y10 if you're in the untreated group. So D here refers to being in the treatment group or not. Okay? Now Q is the probability of being untreated, and P is 1 minus Q, the probability of being treated. Okay? For a random variable X, we will use this calligraphic X, bold X, to refer to the support of this random variable. Because we're going to deal with potentially non-continuous distributions, we will, and not strictly increasing either, we will want to define two quantites. One is the QX minus over the support T. In general, we'll use R in this paper, but other literatures has used the support of the random variable, and then the same for the QX plus. This is kind of another generalized inverse type definition. Okay. We'll also need to refer to the left limit of a function, which is basically the limit from the left of a function that has potentially discontinuity. So we're gonna use this in our bound as well. And finally, when we refer to the range of a function h, specifically that will be referring to CGFs in our context. We mean that we're gonna. This is the values of that h takes when evaluated at y for all y and r on r. Okay. So with that, we can now proceed to define our the copula, which is going to be the main thing we restrict in our set. Okay. So for random variables YT0 and D, we can write the subcopula, which basically links the joint distribution of YT0 and D with the marginal distribution of YT0 and D. Okay. So as a result, because it links the joint to the marginals, this is a scale-free measure of dependence. Okay. So, and I'll give you an example shortly to explain, but the idea here is because regardless of the scale of YT0, FYT0 will go from 0 to 1, and FD of D will also will be between 0 and 1, regardless of how D is generated. For that reason, this is always going to be a scale-free measure of dependence. Okay. So to fix ideas, let's think about an example. Okay. Here we'll think about a Gaussian example with Roy-style selection. So suppose that Y00, Y10, and eta, which is here the treatment effect, okay, are jointly normal with mean 0 and variance sigma. Okay. And here we're gonna think that selection into treatment depends on whether you benefit from treatment or not. So typically following the Roy-style selection type, model. And with that in mind, okay, when we have these conditions, notice in this variance covariance matrix, we normalize the variance of eta to be 1, and for that reason, the covariance between eta and Y00 is rho 0 times sigma 0, where rho 0 is the correlation coefficient between Y00 and eta. And the covariance between Y10 and eta is rho 1 times sigma 1, right? Where rho 1 again is the autocorrelation coefficient between Y10 and eta, okay? So with this here, under this model, we can write FYT0 and D, which is Y, 0, as basically the copula, okay, which is the Gaussian copula in this case, evaluated at the marginal, okay? But notice here that the copula part only depends on rho T, the scale-free measure of dependence here, which is the autocorrelation coefficient, whereas the scale of YT0 is only going to enter in this marginal here. So when we are restricting the copula, we're restricting the autocorrelation coefficient and not the marginal. That's the main thing I would like to emphasize from this here. Okay, that basically we're going to impose restrictions on the copula. And what I want to emphasize is that when we're restricting the copula, we're not restricting the marginals in any way or their scale, but rather just restricting the scale-free measures of dependence between YT0 and eta. Okay? And before I proceed, I just want to emphasize our identification result is going to be non-parametric. We're not going to rely on any specific parametric assumptions on the copula. Okay? But this is just an example to in a well-known distribution as to what we're going to be restricting with. If we have normal random variables and we restrict the copula, what would be restricting as part of this joint normal distribution? Okay. Questions? Any?
No, not yet. Please.
Okay. Great.
Yeah.
Awesome. Wonderful. Great. So now let me walk you through our assumption exactly. Okay. So the copula of Y00 and D, what we're going to assume is that it's going to equal to the copula in the second period as well, the post-treatment period, Y10 and D. So what does this mean? The copula stability here means that we want the dependence between YT0 and treatment, okay, to be stable, and specifically at Q, because remember that but we will not observe like D, like for a couple, because D is binary, that we're only going to be able to pin down the copula at Q here, which is which maps to the probability that D equal to 0. So for that reason, we're only going to be restricting the copula, the horizontal copula at Q, but Y00 and D and Y10 and D here, the copula will assume that horizontal copula for any U will be the same across time. Okay? So first, why is that assumption useful for our goals? As I mentioned earlier, we want an assumption that will not restrict the type of FYT0, and as I will show you, using this assumption, we can provide the unifying identification result. As I mentioned, just the previous slide with that example, when I'm restricting the copula, I don't restrict the marginal distribution of YT0, so it can change in arbitrary ways. And finally, it's gonna be in keeping in with the invariance to monotonic transformations, because the copula will be the same for even if you take monotonic transformations of the outcome. Okay, so that's really like the key point here to emphasize. But before I move on, I think it's very important to think a little bit more intuitively about this assumption, because otherwise it looks a bit too technical. Okay, so to motivate this, remember that we can always disjoint distribution of YT0 and D when D is equal to 0. If we divide it by the probability that D equal to 0, which is Q, we get FYT0 given D equal to 0. So this is the distribution on this left-hand side is the control group's outcome distribution, untreated potential outcome to be precise. And by definition, we can always write it as equal to the copula at Q, the horizontal copula at Q, evaluated at FYT0, okay, which is the marginal distribution that is it. So one way to think about the copula is actually it is a mapping between the conditional distribution and the marginal distribution, right? Where the marginal here, we should think about it as it's the distribution when we average over the treatment and control, okay? So what copula stability is really assuming then is that this YT0 and D, this copula, is stable across time. Remember, Q doesn't change over across time because it's just the membership to the group. So as a result, this is delta 0 equal to delta 1, right? So as a result, what it's assuming is that there's a stable rank mapping between the control group and the marginal distribution, right? So it doesn't restrict the marginal, but what it's restricting is really that there's a stability in the rank mapping between in the control group, right? The rank in the control group and the rank in the marginal distribution, okay? And remember that what if I observe FYT0 given D equal to 0 and YT0 of Y here is not observed, but if I can learn something about FYT0 of Y under this assumption, then I can back out my object of interest, which is FY10 given D equal to 1, okay? Because that's just a function of this marginal and the conditional, okay? And perhaps it's helpful to actually see quickly what the parallel trends is, right? How do we take what I just said about the copula to parallel trends? In fact, the parallel trends assumption can be stated equivalently as a stable difference in expected outcome between treatment and control group distribution. So basically, like what I had earlier is basically the conditional distribution for the control group is equal to some stable mapping of the marginal distribution, right? But here, what we have is not the stability in that ranking, but rather is stability in the difference between the control group mean and the marginal mean. And this is basically the parallel assumption, right? It's assuming that if you take the control group's mean and the average between the treatment and control in each period, there's a stable difference in mean that is going to be the same across time. Okay? Questions?
Yeah.
No questions?
Okay. No questions yet, Dalia.
Okay.
Yeah.
Perfect. Okay, great. All right. Wonderful. So now that I hopefully given you some background and kind of one way to provide an intuition for our copula stability assumption. Another way to think about it is actually copula stability could be equivalently viewed as, could be viewed as, not equivalently, but viewed as a dependence stability assumption, which is simply a dependence version of parallel trends. So parallel trends can be equivalently viewed as a covariance stability assumption. So for a given transformation G, we can write parallel trends as equal to, as this in our notation, right? It's the difference in the untreated potential outcome across time for the treatment, and the control is the same, okay? Now, actually, we can write this equivalently as the stability of the covariance between Y00 and D, as well as Y10 and D, okay? Once we see it this way, we actually realize that, our copula stabilities, instead of restricting the covariance, we're actually just imposing this condition on the scale-free dependence mapping, right? So I guess that's like one of the key takeaways here, because notice that the covariance will be a joint restriction between the marginal and the copula, whereas our copula stability assumption will just simply be is simply restricting the scale-free dependence measure. So one thing to emphasize, however, is that parallel trends and copula stability are generally going to be non-nested. So, for instance, in the Gaussian example that we had earlier, okay, let me go quickly here. In this Gaussian example, copula stability will say that rho 0 is equal to rho 1, whereas the parallel trends assumption will be rho 0 sigma 0 is equal to rho 1 times sigma 1. Okay, so as you can see here, they're different because this can hold while this doesn't, and vice versa. But the main difference is that the copula stability will only require the stability of the scale-free measures of dependence, whereas the parallel trend assumption is really a joint restriction on the copula and the scale of the outcome. Okay?
Mm-hmm. So comes one quick question,
yes,
Dalia, if you don't mind, if you go back one slide. So if you go back the slide before this one, where
I went here, I think, here.
No, again, the one before that. No, it's where you had both the comparison of a copula stability and the trend. Yes.
Yeah,
Okay.
here.
So
yeah,
should we assume that your results are both driven by copula stability or parallel trends PT? Both or one of them?
Oh, no, we're not using parallel trends at all. We're not going to use parallel trends. Okay. We're only going to use copula stability, particularly because, no, we're not going to assume anything about parallel trends. We are not imposing that parallel trends should hold. No, we're only going to assume copula stability.
That's the one driving
this is why in this example, I was saying that we're going to only, if we're using copula stability in this Gaussian case, we'll only assume the autocorrelation coefficient of eta y00 and eta y10 is the same. Whereas if you assume parallel trends, you have to assume that the product of rho 0 and sigma 0, so that covariance, remember this is the covariance in this case, that the covariance is stable. So we're not going to assume that at all. We're only going to, because if you assume both, then you're basically assuming that sigma 0 is equal to sigma 1 as well.
Okay, thank you.
Yeah. So for that reason, no, we will not assume parallel trends at all. In fact, our goal is to move away from parallel trends.
Excellent.
Other questions?
None, not in the chat. I can't. No.
Okay.
No hand up yet. Yeah. Let's continue.
Okay.
Yeah.
Great. So now we I hopefully give you some intuition on our identifying assumption. But again, questions are super helpful for us because we're definitely working on improving the empirical motivation here behind this assumption. And then the next step is for us to actually walk you through the partial identification result. Okay. So here, let me first recap quickly how things work in different diff. and then I will go to us. So again,
I'm sorry.
not doing this.
Could I interrupt you
Yes.
for a second? Just
Absolutely.
yeah.
Yes.
So hi, I'm Jaydeep. I'm trying to figure out one thing because the assumptions seem to make sense, but I still can't visualize an example where this is sort of relevant in the sense of like this correlation being the way you set it up. Is there an example you can give us that will sort of make it more empirically applicable?
So I'm gonna give you more examples, but I guess I would like to understand: are you saying an example that's not what not like so? I guess in the Gaussian example,
So for example,
I'm basically telling you what we're assuming. What would be rho 0 equal to rho 1?
Yeah, I get that, and that's exactly what I'm saying. So when do you see rho 0 equal to rho 1?
So we can't see so if we only have 2 periods, we can't test that, right? But if we have more than 2 periods, then one could test. Or what we're actually working on an extension where we allow for multiple treatments, and then if you multiple periods, and if you impose copula stability on multiple pre-treatment periods, then you can construct bounds that will only be true if copula holds on both periods. But yes, you could test it, but of course with only 2 periods, unfortunately you couldn't. You could test it on parts of the range. So I'll get to this actually when I'm talking about the identification results. So hopefully that will help.
Okay.
And I'll have more pictures in a minute. But at least in the simplest case of a parametric model, in the Gaussian case, here, we'll just be assuming that the rho is stable across time. We could not, in general. I guess if you have a rich enough if you impose, so we're not going to impose a parametric model, right? So that's why we're not going to be able to test it necessarily. But if you were to impose a parametric model, you could obviously estimate it. But in general, no, we can't. No, the problem is like the second period, we can't. Yeah, we can't observe the marginal distribution, so we can't actually. That's the problem. We're trying to identify. We're trying to use this assumption to identify the counterfactuals, so we can't actually test in that case. But if you have more than 2 periods, then you could test your assumption. Yeah.
Okay, thanks very much. Yes, proceed. Yeah.
Yeah, perfect. And I'll provide more examples, and hopefully this will help. So let me quickly, what I want to do before I go into our identification result is quickly recap what it would mean for what we're doing, like how the parallel of what we're doing in the difference in different settings, in case it's helpful. So basically, in the standard definitive setting, right? Like we typically think of it as, okay, we look at the change in the control group and difference it out from the change in the treatment group, right? But the way we're gonna, use the 2 periods in our setting will be more similar to this approach, which is equivalent in the difference world, which is basically, let's go first to the pre-treatment period. We're gonna learn in the pre-treatment period about this difference between the treatment and control group, okay? And now we'll transport this difference to the post-treatment period to identify the counterfactual, okay? So this way of thinking about parallel trends, which is first, let's use period 0 to learn about the difference between the treatment and control, and then transport that difference to the second period. This is going to mimic a lot what we're doing in our identification in the case of our copula stability approach, okay? But of course, we're not looking just at the expectation, but rather what we have here, and this is the minimum wage example. Suppose that we have 2 different groups of states. One has the control and the treatment, okay? And both of them had a pre-existing minimum wage. This is in light of our application, this is like a $7.25 minimum wage. So both of them have a $7.25 minimum wage before the treatment in the pre-treatment period, okay? Now, in the post-treatment period, we observed the control group. It still had 7.25 as the minimum wage, but you can see that the distribution changed across time, right? What we're trying to learn here is this counterfactual of FY10 given D equal to 1, okay? So back to Jadib's question, the main issue here, why we can't just directly test the copula stability assumption, is that we don't observe FY10 given D equal to 1, which would be crucial to identify the copula, okay? So the whole point is, this is why what we're going to do in our setting is actually use the pre-treatment period to learn about the copula. So our first step will be use the pre-treatment period to learn about the copula, and then transport this dependence that we learned about from the pre-treatment period to the second period to exploit what we observed, which is FY10 given D equal to 0, to allow us to identify the counterfactual of the treatment group. Of course, remember, we observe a post-treatment outcome for the treatment group, but that has the treatment, so that's not the counterfactual we care about, because what we can observe something that's with the treatment, what we need is the counterfactual to be able to do policy evaluation. Okay? Jadib, is this example more helpful? And I'm gonna go now through the actual identification result.
Yeah, thank you. It's making it's coming together a little bit now.
Yeah, so this is basically what these are the three distributions we observed, and we're gonna try to learn from them. So I'm gonna walk you through the steps in our identification approach.
Perfect.
So as I said, the first step is to use period 0 to recover the dependent structure between FY00 and FY00 given D equal to 0, which are basically the marginal distribution of Y00 and the control group's distribution, okay? Now, remember that these are related in this specific way, right? FY00 given D equal to 0 is equal to 1 over Q copula Y00, comma D, evaluated at the marginal, okay? Now, by Sklar's theorem, right, we only uniquely identify a subcopula on the range of FY00 of Y. And the range, remember, is the values that FY00 takes when Y is evaluated on the real line, right? So for that reason, in our minimum wage example, so as I said, if we have a Gaussian copula, we would just estimate the rho, right? Or identify the rho using the pre-treatment period. But we're not going to assume parametric models. So what we're gonna do is we're gonna basically uncover this dependent structure, okay? This is the first step in our approach, okay? But remember, because we have this jump here, okay? And because we have a jump, we don't have continuous outcomes, we can only partially identify the dependent structure. Actually, there is a part here in the copula that we don't know what the values are, okay? So now we transport this dependence to the next period, okay? So, and we invoke copula stability. So this is why, again, back to Jadib's question, if we go to the second period, we can't, if we're even in a parametric model, we can't identify row 1, because row 1, by definition, would require us to identify to observe the counterfactual that we're actually trying to identify. So we can't do that, okay? But what we can do is basically invoke the copula stability. What we will do is like invoke the copula stability, transport the dependent structure from the pre-treatment period to the post-treatment period to try to bound FY10 given D equal to 1, okay? So what we observe in period 1 is the control group's outcome distribution, right? That's what we are able to observe, okay? By definition, and by the Sklar's theorem, this is gonna be equal to 1 over Q of the copula of Y10, comma D, evaluated at the marginal. Remember, I can't observe this marginal FY10 because to observe this marginal, I need, remember, this is going to be the probability weighted average of the treatment, which I don't observe, untreated potential outcome, and the control, which I observe. So we don't observe that, okay? But what we can see here, right, is that this here is the copula again. I didn't invoke copula stability yet, but if I do invoke it, now I can transport the dependence from, like the relationship we learned about from the pre-treatment period, 1 over Q, CY00 and D. And from that, if we were, so the first thing to think about, suppose that we had a continuous outcome. If we had a continuous outcome in the pre-treatment period, we could observe the copula everywhere, okay? And we're done. We basically have point identification in that case. If it's a one-to-one mapping, we can point identify what we care about. But the whole problem is that we're settings where we don't have continuity necessarily. We're not assuming actually any specific outcome distribution, which makes this challenging. So as a result, there are several situations, okay? So first, if the range of FY00 is a subset of 0, 1, so as we are here, okay, it really depends what ranges we observe in the post-treatment period, okay? If we have the control group's range, okay, if we observe 0.6 here in the control group, FY10 given D equal to 0, suppose that the specific outcome value, we have 0.6, right, in the control group. This mapping tells us we know exactly what is the marginal value that goes with that, okay? So if we observe parts of the range of FY00 given D equal to 0 in the post-treatment period, we know exactly what the marginal value that maps to them, okay? So we know the marginal value for that Y. The main problem is outside of this range, like if we're in this component here, the problem is we don't actually know exactly where the copula value would be, okay? There is actually multiple ways to extend the copula in this case. Outside of this range, there's the intersection of those two ranges. There's multiple ways to extend the copula. We impose strict monotonicity, and under that assumption, this is going to be the kind of, roughly speaking, the bounds on the copula, like all of the copulas we could possibly extend with are going to be in this bound here, okay? So this is the main idea behind our partial identification result, and the main source of basically where the partial identification comes in, which is basically when we have non-continuous strictly increasing CDFs, then it is possible for us to have gaps in the range of our marginal, and as a result, we will not be able to identify the copula everywhere. And because we're not imposing parametric assumptions, we can only bound the copulas outside of those ranges, as we do right here, okay? And that's exactly why, in general, we have this partial identification result. So in the context of our example, this is what our bounds would look like. The dashed dots here are actually, this is the true counterfactual. In this numerical example, this is the true counterfactual because I can actually compute that one in a numerical example. And then the upper bound is the dotted blue line, and the red line is the lower bound that are defined by our result. While we understand this is the upper and lower bound look a bit complex, but we are really trying to make sure that we have upper and lower bounds that are right continuous. If we take the inner components here, which are just defined on the support, and they would not actually result in right continuous CDFs. And in fact, because we are going to use social welfare treatment effect parameters, that will rely on relying on using these bounds to actually bound the quantiles and integrate over those. It's really crucial for us to have upper and lower bounds that are right continuous. And it's also important for the sharpness of our bounds. Okay?
Okay.
Great. So what I want to do next context is basically talk a little bit about the connection to AT and INVENT's changes and changes approach, because in fact, there's some really interesting connections there. And then I'll proceed to talk about the social welfare treatment effect parameters and then the application. Okay? So in seminal work by AT and INVENT, this changes and changes approach was introduced. And I want to mention that, of course, if you look at our bounds, they do look, they resemble a lot of changes and changes. So it is curious to understand what is happening there. So what we actually realize is that for strictly increasing continuous CDFs, the bounds actually simplify to the point identification case of the changes and changes approach. And in fact, for this class of distributions, copula stability is equivalent to the changes and changes conditions. It's very intuitive. Why? Because basically, if you have a strictly increasing continuous CDF, there's always a strictly monotonic function that can take on the values of that will basically can be used in this context, and the margin, like the copula stability, will be basically the main condition between the U and the unobservable in that case, and and it's basically straightforward from that perspective. Okay. Now, and on the other hand, copula stability can be compatible with multidimensional heterogeneity. So we have one example here that I want to walk you through. So first of all, as I mentioned, that copula stability for continuous strictly increasing CDFs will be equivalent to the changes and changes model. And just let me walk you through why it's actually very intuitive. So if we show that these two statements are equivalent, copula stability and this having a strictly increasing function, because basically we can take HT to be the quantile in this context, and the quantile here will be strictly increasing. We can define the unobservable U as the CDF evaluated at the outcome, and that will be a uniform 0-1 for both time periods. So we're already starting with a marginal distribution of the unobservable that is time homogeneous. So as a result, just adding copula stability will give us this time invariance condition that comes from AT and INVENT. Okay. The other thing I wanted to mention, as I said, is that and this is something, an aspect of the paper we're still working on. It's basically to show that there are at least some models where we can show that our conditions could handle broader sets of models than the changes and changes result. Specifically, consider this binary outcome example, which is a flavor of a double hurdle model. So suppose that the treatment is equal to 1 if the unobservable V is greater than Q. And then YT0 is going to be 1 if both U and UT tilde are below a certain threshold, are above a certain threshold, but they're going to be 0 otherwise. Okay? So this is a case where we can actually allow for multidimensional heterogeneity. And in fact, we can allow for more than just 2. It's easy to see with binary outcomes how one could extend this result beyond that. And in this case, actually, if we assume that the copula that governs the dependence between UT tilde, and V is equal to this type of nested structure, then here we would be able to basically show that this type of model would be consistent with our copula stability assumption. But if you recall, the changes and changes assumptions in AT and INVENT for discrete outcomes require monotonicity, weak, but still monotonicity in a scalar unobservable. So basically here we can allow for multidimensional heterogeneity. And as I mentioned, this is an aspect of the paper we're still pushing forward. So we are hoping to have more results in this in the future. But so far, this looks promising that basically, while we are going to get something that's equivalent to the changes and changes assumption for strictly increasing and continuous CDFs. We have we can allow for multidimensional heterogeneity with the copula stability assumption, at least for binary and discrete outcomes, whereas that's not allowed for in the standard changes and changes approach for discrete variables. Okay, so one other thing I want to mention is basically, again, that's important in comparing to changes and changes. In the context of our bounds will apply to any of these types of outcomes. So whether you have a discrete outcome, bottom coding, top coding, or bunching in the middle, as was more typical in the context of the in our application, all of these our bounds apply to in a straightforward manner, whereas the changes and changes bounds only apply to the discrete outcome. So this is because they don't have bounds in for bottom, top coding, and bunching. For discrete outcomes, in numerical applications, numerical examples, we find typically that our bounds and the Athia embeds bounds coincide. So even though we can handle a larger set of models, our bounds are, in numerical examples at least, very similar, tend to give us very similar results. One thing I do want to mention too is that for mixed outcome distributions, naive implementations of the changes and changes approach can actually lead to false point identification. Because in the context of mixed outcomes, their bounds might actually be, the upper and lower bound might be equal even in settings where we don't necessarily have point identification. So as a result, basically, for instance, in this bunching example, what we can see is that their upper bound and lower bound would equal to the blue line here. So making you think like this is a point identified result, whereas actually this will not include the counterfactual distribution. So one thing to keep in mind is just that we are able to handle all types of mixed outcome distributions and also discrete distributions without having to change the definition of our bounds. That's really one benefit of having unifying partial identification result in this context. Sounds good? Other questions?
Yeah, so you seem to conclude on this one in favor of copula stability, in favor of CS compared to changing the changes, right?
Sorry, can you repeat your?
You seem to conclude in favor of comparing the two when you are doing a comparison between CS and CIC. You seem to favor a CS.
I mean, I think that I don't want to seem like I'm in favor of one over the other necessarily, right. But I think it's important to keep in mind that, of course, the structural assumptions imposed in the changes and changes paper are very useful and are. But I guess what we obtain here is actually so just to be clear, like in the changes and changes paper, there is no all the different outcomes with mixed outcomes are not at all handled. So the comparison is really for the discrete case, okay? Continuous and strictly increasing outcomes, we're equivalent, so we can't really there's no real meaning of comparison. For discrete outcomes, what we are able to show is that you can handle multidimensional, unobserved heterogeneity, and I think that is actually can be very important because while the structural assumptions can be very useful in certain settings, for instance, in other work with Désiré and other co-authors, we actually use these structural assumptions from changes and changes to conduct attrition corrections and to allow us to extrapolate alternatives. So the copula stability assumption would not be strong enough to be able to allow us to do that, okay? But I think even in this work, we noticed that it's hard to justify for certain outcomes why there's a scalar that's unobservable that's determining the outcome. So the structural assumptions in some settings can be very hard to justify. While they're very useful and can be very helpful in identifying maybe even more things than what we can do in this paper, I think it is important to keep in mind that in some settings it can be very helpful to be able to allow for multidimensional heterogeneity. For instance, for a binary outcome, they're usually, for instance, think about female labor participation or going to college. These are there's typically multidimensional factors that lead to you deciding to on a 1 or a 0 for those outcomes, right? So for that reason, we think that being able to handle multidimensional heterogeneity with copula stability is obviously a benefit, especially in reduced form settings where we may not want to assume too much on the structural or the production function of our outcome.
Excellent. Okay, let's proceed. I don't see any hand ups, so let's proceed.
Okay, perfect. Okay, so now I can give you a broad overview of our social welfare treatment effect parameters, and then I'll go to the application and illustrate what they look like and kind of use them to help us understand why it could be useful to look at the counterfactual distribution. So, the social welfare treatment effects parameters we're thinking of. So the way we're going to want to compare the social welfare function, okay, evaluated at the observed outcome for the treated group, right, which is Y11, and the counterfactual that we partially identify using our approach, right? The class of welfare functions we're going to look at can be written equivalently as the integral over a weighted quantile, okay? So the class, so just, I know this looks too obscure, but let me actually first start with, suppose that this weight is equal to 1, okay? Then actually this gives us the utilitarian social welfare function, right? This utilitarian social welfare function gives equal weight to everyone in our distribution, regardless of their quantile, right? And as a result, this results into a kind of an inequality neutral social welfare function, and the average treatment effect on the treated would be the social welfare treatment effect parameter implied by this social welfare function, okay? An interesting alternative that allows for equality kind of considerations, and this here we built on relevant literature in this context, is one where if we allow this omega of tau to be 2 man minus tau, then we can show that the social welfare function for any distribution will be equal to a product of two things: the expectation of the outcome, or x in that case, and 1 minus the Gini coefficient that we all have learned even as undergraduates, right?
Yeah.
So,
yeah.
right?
Yeah.
So that what is neat about the social welfare function is that what we can see here is that if you hold inequality constant and increase the expectation of x, social welfare increases, right? But if you hold the expectation of x constant and increase the Gini coefficient, which means we are increasing inequality, social welfare is lower. And notice that if we have a complete inequality in that distribution, so if the Gini coefficient is 1, then the social welfare function is 0, right? So for us to have this component, here is 0, regardless of the expectation of x. So as a result, if you have complete inequality, increasing the expectation will not change the social welfare function, right?
Mm.
And so I think this is important to keep in mind, that this is a neat social welfare function that will not just increase based on increases in the expectation, but also reductions in inequality. Okay?
Okay.
Any
Yeah.
questions about that?
No, not yet.
Okay, cool. So now I want to mention that, as I mentioned in our application, right, we expect to have most of the action, so to speak, that our policy will induce will be in the lower tail. So actually part of this distribution will be completely unchanged, right? So we may want to zoom into that lower part where the action is happening so we can actually get meaningful results. Perhaps if you're at the very bottom tail, that where things are changing, if you just look at the average, as I mentioned earlier, you may not actually see much of a change, but maybe people in this lower tail that are affected by the policy are experiencing greater changes, right? So for that reason, we also consider lower tail social welfare treatment effect parameters, and specifically two that I think are most useful here. The first is a lower tail average treatment effect on the treated for a given quantile U, okay? So basically, if we allow XU here will be the quantile of V, where V is basically a uniform 0 up to U, okay? So what that does is that it's gonna only look at the lowest, say, 10% of the distribution and try to capture the impact on the mean for that lower 10% of the distribution. So suppose that, I mean, this is more than, this looks like the lowest, like, I don't know, 40% of the distribution. So if I compute in that case, the lower tail, 40% of the distribution, we see that what it looks like is that the mean will have changed a lot, right, for those lower tail. And it allows us to zoom into the changes in that lower tail of the distribution, which we care about for policies like the minimum wage, right? And just to be clear, this can actually be adapted to any part of the distribution. So for instance, in pollution monitoring, the policies typically target other parts, not necessarily the bottom part of the distribution. And for that reason, it's important. We're able to also allow for that for any interquartile range, actually. And that's in the paper, as I mentioned here, okay? Similarly, we can also look at the lower tail Gini social welfare function. So this takes the very similar shape as the one I mentioned earlier, but instead of just looking at the entire distribution's social welfare function, we're looking again at this lower tail of the distribution, okay? And I think some of these concepts will be easier to understand when we go to the application, which we will go to shortly. But let me pause here briefly in case there are follow-up questions.
No questions. So good. Please, yes, continue, Dalia. Yeah.
Okay, great. So now, what we are left with is really trying to go over the empirical application and hopefully illustrate to you the method compared to existing approaches, etc. So, we're going to revisit the setting in Sengiz et al. 2019 QJE paper for empirical illustration. I want to just emphasize that they examine like the impact of 138 state-level minimum wage changes. And for the purpose of our application, just to keep it succinct, we're going to focus on 2 years, 2010 and 2015, okay? And we look at the treatment group as the group that experiences an increase of at least $0.25 in their minimum wage, zero otherwise. And also we're going to look at the subsample of states with pre-treatment minimum wage as greater than $8 for the purpose of our this application. The remaining subsample is actually in the paper, okay? A few things to highlight about this application. So they rely on the individual level MBR merged outgoing rotation group. So this data set is actually, especially when we look between 2010 and 2015, this will be like a repeated cross section. It's not going to have a panel approach. So that's when I mentioned earlier that what we really care about is an approach that can handle both repeated cross sections and panel data. It's really because in our context and the context we care about, we may not actually be able to we would not be able to get at these other, and we're not going to be able to apply them if they require panel data to this data. Okay.
So,
and as I mentioned, yes.
So this previous paper on which it was using a different approach compared to yours, and you want to see whether the results will resonate.
So we are not. So they use a regression approach that tries to get at, basically tries to estimate this excess jobs, missing jobs. Like their parameters that are delta A. Actually, that's a great question. So what they're trying to look at are very specific parameters, which are basically how many jobs were created above the minimum wage, how many jobs were lost below the minimum wage, and then that allows them to look at the change in employment, which is delta A plus delta B. Okay?
Yeah.
We're not going to look at that only. We're going to try to identify the whole counterfactual distribution to try to, but that we're going to revisit their parameters using our approach.
Yeah. Okay.
But we're not. But I just want to clarify: we are not going to exactly replicate their approach. We're actually going to compare to existing methods in the econometrics literature.
Fair enough. Yeah.
Okay.
Yeah.
And just a reminder here that basically, again, this is the setting we're thinking. This is their conceptual framework. They're expecting a minimum wage will be impacting the lower tail of the distribution and may not have any impact for most of the distribution, actually. So we'll keep that in mind, because when we look at the treatment effect parameters, I'll show you, you'll see that maybe when we aggregate over the entire wage distribution, we might not see much happening. But when we zoom into the lower tails, we will see that there is more of an impact. Okay? So what am I going to do here? I'm going to first show you the counterfactual distribution and compare it to the distributional difference in differences. Okay? This is an approach that technically can work for mixed outcomes, but I will show you that it can have some issues in our application. And then I'll go to our welfare parameters that I introduced earlier. And then finally, I'll also go to the parameters in Sengiz et al. Measuring employment changes around the new minimum. Okay? Before I proceed, as I mentioned earlier, the distributional DID, this requires some strong assumptions for it to hold. And in fact, it has a testable implication, which is basically that the counterfactual distribution you obtain from the treatment, for the treatment group, should be monotonic, right? So if we are using an approach to identify a counterfactual distribution, we expect it to be monotonic and integrating to one. Okay? So now let me first compare our bounds here to the distributional difference in differences. Okay? So what we can see is that our bounds are able to look like CDFs, right? Whether you look at the lower or upper bound, they both look like CDFs. I can assure you they're right continuous. The picture may not show it, but they're right continuous, and they're strictly increasing. Sorry, they're not strictly increasing, but they are monotonic. So they are weakly increasing, right? When we look at the distributional DID, we see that it can actually violate monotonicity. And in fact, it violates monotonicity around the minimum wage change that we are experiencing in this sample. So here, we have states that were about $8 in minimum wage. That was their pre-treatment minimum wage. And the black line here is the post-treatment period. And you can see here that some of them, like above 9 is basically the new minimum wage for a significant proportion of the wage earners here. Okay? So what I just wanted to take away from this is clearly there is violations of monotonicity around the pre-treatment minimum wage by the distributional DID, whereas looking at our approach, we can see that we are, don't have these issues because by construction, our bounds are monotonic and are also, look like are guaranteed to be CDFs. Okay?
Okay.
Yes. So now moving on to the social welfare treatment effect parameters. As I said, I'll first give you the treatment effect parameters for the overall distribution, and then I'm going to look at the lower tail to zoom into kind of the part that is most affected by the minimum wage increase. Okay. So first of all, the Gini social welfare treatment effect on the treated can actually be composed in two components, a mean component and an inequality component. Okay. The mean component will basically be the ATT times 1 minus the Gini coefficient. So let's first look at the ATT. What we see here is that we see the average wage in the treated states is about $25.83, okay, post-treatment. And according to the CS, the copula stability bound, the increase from the minimum wage is between 12 and 56 cents, right? So is that surprising? Of course not. If we look at the average of the entire wage distribution, we may not think that the minimum wage increase will increase the average of everybody in the distribution very much. And this is consistent with what I mentioned earlier, is for policies that target specific parts of the distribution, these measures that look at the entire distribution may not be capturing the most meaningful quantities impacted by the policy. Okay? When we look at the Gini social welfare, on the other hand, same thing. It looks like, you know, we have this very small change here, and we look at the two components. Again, they're very small changes, and you know, possibly between like for the inequality, we can't even, like, the sign is not determined. Okay. One thing I want to mention is that the inequality component, I'm going to use outer set bounds here, and these are not going to be sharp, but at least it gives us some idea of what's happening with the inequality component. Okay. Now moving on, let's zoom into the lower tail and see what happens in that lower tail. Okay. So the lower tail mean, what we can see is that for the lowest 1% of earners, we see significant increases, right? About 1.59 to 1.68. And you can see, even though these are bounds, they're actually very, like, in terms of quantity magnitudes, they're very close to each other, right? 6.15 for the 2.5%, the post-treatment, the 2.5% lowest earners are earning about 6.15. And according to post-treatment and according to the social welfare treatment effect on the treated, this is about $1 of an increase attributable to the policy. And finally, the lowest 5% will be are earning about 7.57 post-treatment. And according to the social to our CS bounds, 60 cents to 91 cents of this is attributable to the minimum wage increase. Okay. As I mentioned, the distributional DRD has some monotonicity violations, and we can even see that some of the quantities that it estimates are actually even outside the bounds that we have here. Okay. Now, looking at the lower tail Gini social welfare function, and again, I can decompose it into a mean component and an inequality component. We can see again that there are increases for all of this lower tail in terms of mean. And the cool thing that we can also see is that there are not just the increases in the mean, the increases in the Gini social welfare function are not only due to increases in the ATT, but also reductions in inequality. Okay, because remember, if there's no change in the inequality, then this delta I would be 0, right? But what we see here is that basically the bounds on this delta I that we estimate are negative, both upper and lower bound, and basically for all these lower tails, and we have the mean also is increasing. So we have both components. So basically the takeaway here is that what we see from these measures is that the lower tail is benefiting both in terms of increases in the mean and reductions in inequality due to the due to the minimum wage increase. Okay?
Okay.
Sounds good?
Yep. Perfect.
Perfect. Perfect. Okay, now finally let's take a moment to look at the quantities, because as I said, the Sengiz et al. Paper are really focused on these like changes in employment above the minimum wage and the below the minimum wage, right? Whereas we are looking at the whole distribution and we're trying to look at different parameters, but we can also compute the parameters from their analysis. Of course, one thing I want to mention is we focus on two years in their sample, and a few minimum wage increases. So we want to emphasize, of course, that this is really like not directly comparable to their quantities, but we actually get very similar conclusions. It's not that different. So in terms of delta B, this is the percent of employment, right? The change in employment below the minimum wage, right? When we compare the observed with the counterfactual distribution. And what we can see here is indeed that, our CS bounds estimate between a reduction of employment here of 2.9% up to a marginal increase of 0.3%. So either the employment here is reduced by almost 3% or basically didn't increase, like or marginally increasing by 0.3%. Okay. Now, in terms of the excess jobs, the delta A here, we asked that our bound suggests that there is either no change or an increase of up to 2.3%. Okay. One thing I want to mention here is that basically post-treatment, there's 2.3% employment below the minimum wage. There's 16.6% employment in this range here, okay? And what we see is that our estimates suggest that this 2.3% is reduced relative to the counterfactual, more like, or margin, or didn't really get affected by the policy. And the 16.6% either did not get affected by the policy or increased maximum. 2.3% of them are attributable to the minimum wage increase, okay? When we look at the overall change in employment, so we're looking at the change in employment in this range here, okay? The neat thing is that we see that there's basically no change, okay? So it's either a reduction of 0.6% or the upper bound is zeros, which basically suggests no change at all, okay? So this is broadly consistent with the conceptual framework in Sengiz et al. That basically a minimum wage increase could increase employment above the minimum wage and reduce employment below, but the change overall in employment would cancel itself out or not really, or increase or decrease marginally. But yeah, so that's broadly consistent with their result. Okay?
Excellent.
Questions?
No. Fine.
Wonderful. Okay,
Yeah.
So let me conclude and then we have time for kind of more big picture questions, hopefully.
Okay, yeah.
So, broadly speaking, as I mentioned, the motivation of this paper is the evaluation of regulatory policies that take this shape of a threshold type policy. And what we note is that these policies tend to induce behavioral responses that lead to mass points and outcome distributions, right? We propose a unifying framework to identify counterfactual distributions in different settings that are very suitable for, identifying counterfactual distributions for these policies. where we are interested in methods that are invariant to monotonic transformations of the outcome, apply to any type of outcome distribution, whether continuous, discrete, or mixed. Because as you saw in our when you look at data, it sometimes can be very hard to see, is this a continuous or a mixed outcome? Like, it's not easy to actually tell from just looking at data. It's not always very easy to have to take a stance on this. And finally, we exploit this copula stability assumption. This assumption really relies on the stability in the dependence between selection into treatment and the untreated potential outcome. If you buy this assumption, then our approach is able to provide you with sharp bounds on the counterfactual distribution, does not rely on any parametric assumptions. Okay?
Okay, great.
Our bounds can then also be used to bound a broad class of social welfare treatment effect parameters, and we show the empirical relevance of this approach and the parameters that we're interested in the context of a recent minimum wage study. And thank you very much for listening. And I hope we have time now for some questions, but also feel free to email me if we don't have time to go through all questions. Thanks.
Okay, thank you. So let us put our hands together and thank Dalia for presenting the paper, presenting complicated stuff in such a straightforward way that we got excited and interested, and we carried along all the way to the final conclusion. It's absolutely interesting, fundamental, and it's one thing whereby basically you follow the story, you follow the tough mathematics, and you become excited as you go. Excellent, interesting work. Yeah, in fact, for me, the most interesting aspect of the work was just to say, regulatory policies, and then go straight into the deep end of the UNESCO exposition, cite the relevant. Yeah, that's what the deep end, and I came out to breathings, so that's okay. I didn't stay in the deep, and of course, the huge literature that you invoked to illustrate the point, and finally, illustrating the example of how this works. Very, very important concepts. In here, I was saying change in changes, and then now difference in differences. So there was a lot of terms in vogue, but the work is extant. It is, this is the main threat of, where researchers, including the researchers in this group, should go. Now, I'm not trying to take you a little bit out of your case, the example you used for illustration, which is the minimum wage. And of course, minimum wage has been controversial in economics, in labor economics, especially for a long time. And you breathe some new life into our understanding of how it works, and especially the social welfare implications of it. Now, I'm just thinking, I was trying to all the way follow the story, and I think that's where excitement came in, drawing from examples in banking and finance. We know since the introduction of Basel I in about 1985, that's when Basel I was put there, and it's introduced for regulating all the banks around the world, okay? And you just have a level playing field of looking simply at the capital adequacy. Say a bank has to have capital adequacy minimum ratio of 8%.
Yes.
And all around the world, the banks jump up and down 8%. The supervisors would just go into the banks and bulldoze them, supervisor from central banks. Now, however, a little bit, the financial crisis hit. I think that was called the Asian flu. In about possibly 1997, 98, 99. And what it showed that this threshold point of regulation of 8% was not adequate, that banks have to do much more than that. They did much more than that. They looked at some of the different assets And there was, in fact, your metrics, the way I was getting excited about your metrics of where you are showing that has changed, were the way the metrics for bank regulation is constructed in the same way.
Yeah.
Okay.
So like, you mean that picture, the CGFs?
Yeah. And then there came, of course, the global financial crisis. And then moves now to Basel III. Basel III still has entrenched that there has to be a threshold. There has to be a buffer zone for banks. Every bank has the threshold. And so, you will excuse me if I start running away by trying to think that this work you are doing on thresholds might have great relevance for looking at a problem that started in 1985. And even when regulation has changed from Basel I to Basel II to Basel III, a critical element of that is minimum capital requirements. And now there is a fashion, especially in emerging economies. Why going to come even in the UK? That when a new governor of the central bank comes in, he said, no, I think the minimum capital requirement for the bank is very low. And that's why there is likely to be risk. Hike the minimum capital requirements to be, say more than say $50 million. And of course, some banks in some small countries, the banks fall. So I'm saying this story all along to say, to just try to excite you to think, maybe if we're thinking of thresholds and this methodology, maybe it could have some relevance to unwrapping, or maybe I'm thinking of this and somebody else has already done it so well, has hammered it so perfectly.
Well, I think it would be interesting to look. I think that like the more you look around, there's so many threshold policies. They're easy to implement, right? Much easier than many other policies. So I do think it's very interesting to look at these policies. And I think even if, my sense is that folks typically focus on either very specific parameters or average treatment effects. So I think looking at these settings, but with an eye towards the impact on the whole distribution, how did this impact the outcome you're trying to regulate, right? It's very interesting. And I think, it would be awesome if you have some references on these policies, I'd love to include them actually in the paper.
Yeah. It's the distribution of the Z score. The Z score is the measure of risk exposure and risk stability. So when people talk about bank stability or bank stability, they are looking at the Z score. It's so very helpful because it's not kind of like backward looking like most of the other measures. So I would say, the threshold effects on a bank capital, a minimum capital requirements, and the distributions you explore now. You are using the distribution on warfare. This, I think, would be the distribution of the Z score. There are also adjustments of the Z score. Yeah. So maybe if I understood your paper very well, then I could think of just embedding a paper and looking at an idea, that a field that I already work on. It's where I could look at some of the path-breaking papers on looking at Basel, especially Basel III. And to see where there is, interesting. Okay, let me come back to our colleagues here and excite some and invite some interventions or questions or ideas. Okay, I can see Jaideep is a colleague. He's actually 2 offices away from me, although we are sitting in different offices of Kodobacho, but he's a senior colleague here at SOAS. Jaideep, please go ahead.
Thanks, Victor. Thanks, Dalia. So I should second Victor's with comments because in terms of, especially in terms of jumping into the technical bit, but I'm just trying to understand from the intuitive perspective one thing that's not fully sort of clear to me, which is this the importance of this assumption about the selection into treatment and the correlation, the stability of this dependence between the two, and the untreated potential outcome. So, the example you were giving, for example, with the minimum wage and the fact that if you wanted to test it, you would have to look at multiple applications of the policy, right? Effectively, like you would be looking at like multiple interventions potentially.
Yes.
And so, just trying to figure that out. I don't know if that is the case, that there is actually a stability in this case between the untreated potential outcome and the selection and the treatment, when you're looking at progressive applications of the same policy, for example.
You're saying like a new minimum wage,
Yeah.
increasing to minimum wage, but that would be considered a different policy. Like in
Okay.
technically
Yeah.
speaking, because we are treating D as a treatment at 0 or 1.
Okay.
So I think if we consider further increases to, but just to be clear, and this is one thing that's very important here, is that typically there's a pre-treatment minimum wage, right? So I don't think I have all the figures here, but
yeah, you mentioned that, yeah. So
and typically and this is exactly what, because if there wasn't a pre-treatment minimum wage in a way that then you have a continuous distribution potential. But the whole point is we have a pre-treatment minimum wage, right? And then this gets increased further. I don't have here the observed for the D equal to 1, but the treated states would be ones that increase it. So let me try to first, for that setting, what's crucial is, suppose that states that impose this policy are states that tend to benefit from minimum wage increases. Okay? Then I think the idea here is we have to assume that this benefit is not asymmetrically dependent on the pre-treatment or the post-treatment minimum wage, right? So if we think that this treatment effect depends in the same way on the wage, I think you could justify this assumption. But I think if there's a reason for you to think that there is, if the dependence between the untreated potential outcome in the pre-treatment period and the post-treatment period is just different relative to what's driving the selection into treatment, then of course it would not be true. And for instance, let me give you an example. If you thought that the pre-treatment wage is the reason why they're invoking this policy, then there's only very specialized conditions on the dependence between Y00 and D that will allow for you to have copula stability. So you're right that, of course, it's an assumption that imposes structure on this dependence to be able to learn something from just 2 periods that is a counterfactual. So of course it has to be an assumption that's informative about this counterfactual. Otherwise, we wouldn't be able to learn much from it.
Yeah, and it's great because you're actually giving up a lot of other structural assumptions in the process. So you're actually doing quite well in that sense.
We're trying. But it is a hard problem because I think in the end of the day, these static panel type approaches have to invoke some kind of stability across time to be able to learn something about counterfactual distributions, especially when you don't want to, because in these settings, you don't want to assume things that are like random assignment. So really allowing for state level heterogeneity in this context, or individual level heterogeneity, to be unrestricted is crucial, right? So you're left with then imposing some stability condition across time.
Perfect. And I have one other sort of question. I'm not sure it's fully clear, but maybe you can clarify for me. So you use this Gini for the inequality aspect, and you're looking at only a part of the distribution. But to me, even if the other part of the distribution doesn't change, their welfare, if you're taking Gini into account, it changes. In the sense.
Can you help?
So I'm thinking that basically, let's say that there's 2 parts of the population and one part improves and the other part doesn't change.
Yes.
So if you're giving weights to their welfare, then essentially the part that didn't change at all has a sort of social welfare implication, especially.
No, of course, absolutely, absolutely. But I think if I understand what you're saying correctly, these people here,
Yeah.
the fact that we didn't help them has social welfare implications. Absolutely, you're right. Right, that's what you're saying, right?
Yes, and basically that's I think basically by taking only the scale, like rescaling and only taking one part of the distribution, I'm not sure that that's I mean, does it make sense what I'm saying? Like the fact that.
No, I think I understand what you're getting at. So I guess the lower tail social welfare treatment effects on the treated, it's not meant to say, it's not saying that the other measures are not important, but rather that you may not, you may not see much happening. If you look at this overall distribution, you're like, okay, the minimum wage had no impact, right? Which is true. I mean, I think, let's think about it. In a place like the US with such immense wage inequality, right? The minimum wage increase will not affect overall distribution too much, right? So in a way that we're not saying that these measures are not important. Of course, these measures are important. But if we want to understand or quantify the impact on the parts of the distribution that are actually impacted, then zooming into those parts is crucial. That's what these measures. So they're meant to more adequately measure the impact on the social welfare for these parts of the distribution, but they're not saying that these are not important. Of course, these are also equally important. Overall, they help you understand at least, okay, overall, we don't see much of an impact, right? And of course, because you don't want you don't want other people who are other parts of the distribution to lose from it, right? So this seems like, okay, when you aggregate over the entire distribution, the impact seems to be small. But if to adequately measure the impacts, the lower tail matters a lot here. Like zooming into the idea here is really you're zooming into the lower tail while the action is happening. That's mainly the idea, right?
Okay.
It's not saying that the other social welfare measures don't matter. Of course, we should care about everybody from a social welfare perspective. And in fact, if the other part of the distribution was negatively impacted, right, then we would obviously want to capture those. In fact, one of the comments we got is basically the fact that we have to think very carefully about these measures of the lower tail and how the fact that they're policy relevant relies a lot on the other parts not being affected, right? Because if the other parts were affected, then we should not be just zooming into the lower tail.
Okay, so you have to check. Okay, I understood. Thank you.
Yeah. No, I think that's great. That's a great point. Obviously, but the idea here is more like I've seen it also with other like pollution monitoring type policies where if you look at overall, like you don't actually see much of an impact, right? So you say, okay, the policy is not effective or it's not doing anything. But when you actually zoom into the part that you expect the change to happen, you actually start seeing more of an impact.
Yeah, makes sense.
And I think that it's all about quantifying adequately what we're trying to measure. And I think there's also another piece to this, which is to think that if there's two pieces. There's a piece of like a minimum wage will only impact the lower tail, but also if I'm a policymaker imposing a minimum wage, I care about the lower tail, right? That's kind of, they're both related, right? Of course, I want to make sure that the policy doesn't hurt the rest of the distribution, but I might also want to really think or understand very carefully how the policy impacts this part of the lower tail of the distribution as well.
Makes sense.
Thanks.
Excellent. Now, I know we are running out of time, but let me put in one quick question, if I may, Dalia. I'm looking at slide 27, the one you are showing now.
Yes.
And I see you have the mean values. Now, should I assume that these values are generated via simulations? How do you generate these values?
No, so these are values generated. This is actually from the application. So taking the first value here, these are actually the post-treatment outcome for the treatment group. Okay. So, for instance, let's look at the lowest 1% in the state that implemented the minimum wage increase in 2015. There, the lowest 1% earners were earning about 3.63 on average, right? Whereas the 5% of owners in these 2015 treated states is about 7.57, right? Now, the copula stability lower and upper bound are coming from our bounds on the outcome distribution for the counterfactual, and comparing them to the observed distribution. So these measures are basically saying that we estimate the impact for the lowest 1% to be between 1.59 and 1.68 on average. So basically, this is to say that maybe more than a third of this 3.63 is attributable to the policy.
Okay.
Right? Whereas when you aggregate up to say the 5%, you only see a 60 cent to 91 cent increase in this 7.57. I want to maybe clarify one issue. Remember, when we have randomized control trials, we report the average of the control and then the treatment effect, right?
Mm-hmm.
But the problem here is that we don't observe the control group. We don't have a control group, right?
Yeah.
And we can only bound the counterfactual. So this is why I'm reporting the observed outcome post-treatment for the treatment group and the bounds on the treatment effect. So when I compare them, I can figure out how much of this post-treatment outcome I observe is attributable to the policy.
Okay. Would it have worked to use some simulations with starting values? Or that would be...
We actually don't need to simulate.
Okay.
I have a lot of numerical examples in the paper, but we don't actually need to simulate here. This is a point on implementation that I should have maybe gone over a little more slowly. So that is a good lesson for next time. But the nice thing here is can be computed using like the CGFs and the quantiles. So these are all directly plug-in estimators, no problem, right? This limb soup is a bit more. It takes a little bit of computation time, but they're actually not hard to compute.
Excellent.
Yeah.
Okay.
So in terms of implementation, it's not actually. It's fairly straightforward. It's just sample analogs.
Excellent. Let me see if we have any further comments so far. I don't see any hand up, so I see we are completely converted, and very much appreciative for taking us this work, making it seem so easy, making it very interesting, seem so easy, and yet it's very complicated. So you have a very good knack of explaining a very complicated stuff. You should be giving the huge annual the Congress Econometric Society Congress papers. But this which take the keynotes for 2 hours, which Thanks very much, Dalia. We much appreciate sharing.
I really appreciate all your questions.
Sharing the work with us. And please join me to thank Dalia with a hand of applause for this fantastic work. Thank you very much. Thank you indeed.
Thank you, and thank you all for accommodating my time change, and also for being here and all your great questions. It was a pleasure. Thank you.
Yeah, great pleasure. You are starting on a very intense collaboration with Center for Global Finance, so we shall keep you in the loop. And follow all your work through. Thank you indeed, and thank you all of you who are here for this paper. We look forward to seeing you again next week, next Wednesday, 1, 2, 3. Thank you very much. Thank you, Dalia.
Thanks. Bye.